Hi, so in this video we're going to model the vertical mass spring system. Now, the major difference between this and the horizontal mass spring system is that now mg actually contributes to the motion. So first of all, I'm going to model the downward section of this motion. You can easily model the upward section as well, you get the same answer in the end. Now, if we go to our free body diagram, we will have mg pulling us down, and we have the spring force pulling us back up, and so on and so forth. The cycle continues. So let's go ahead and use Newton's law. So sum of forces in y equals ma y with down as positive. Now the equation is going to be mg minus ky equals my double dot. Now remember, we have an extension in our spring, so it's going to be mg minus k open bracket. Just like with the previous example, like we had one side getting longer, one side getting shorter, here we only have one spring, and it's going to get longer as the block moves down. So it's going to be extension plus y, plus because it's getting longer, equals my double dot. Now we have to take a little detour and consider this system in equilibrium. If this block was hanging in equilibrium, so let's say there was no motion, you simply put the block on the spring and let it sit there. The system would be in equilibrium, and because it's in equilibrium, this force would equal this force. But you can prove it. Sum of forces in y equals ma y. Let's pick it down as positive, it doesn't matter because it's not moving. You will have mg minus ky equals m, but acceleration is 0. So in the end you get mg minus ky equals 0. Why are we doing this? We're doing this because we want to find the natural extension, i.e. when you put the block on the spring, where does it naturally sit and extend to in equilibrium? Because that will be your starting position. So equate it, mg equals ky, y equals mg over k. When it's in equilibrium, y will be the extension. The distance moved will be the extension. So E equals mg over k. Now we can substitute this equation into our equation on the left. So we have mg minus k, open brackets. Instead of extension, we have mg over k plus y equals my double dot. Let's go ahead and expand the bracket. So we have mg minus kmg over k minus ky equals my double dot. Now we can clearly see that the k will cancel with this k here. Then you're left with mg minus mg, which is 0. mg minus mg is 0. So all you have left is minus ky equals my double dot. So we have minus ky equals my double dot. Let's put them both on the same side of the equation. Plus ky equals 0. Divide both sides by m. We have y double dot plus k over my equals 0. And this looks identical to our characteristic equation. X double dot plus omega n squared x equals 0. So you can clearly see the system is simple harmonic and the natural frequency is square root of k over m, just like the horizontal block is the exact same equation. Hi, so in this example we have a mass with two springs hanging vertically. So let's start with the free body diagram. Initially, don't forget, we're going to model the motion going down Again, you can model it up, you'll get the exact same equations. Now, free body diagram. So, mg is pulling us down, and we have here k1y and k2y pulling us back up again. The motion is simple harmonic, so we'll keep oscillating forever. There's no damping in the system. Now let's go ahead and use Newton's law. So Newton's law states that the sum of all the forces in your system in the y direction equals ma in the y direction. Since we're modeling the downward phase of the motion, we're going to take down as positive. So we have mg minus k1y minus k2y equals my double dot. Now, let's include the extension in our modeling. So we have mg minus k1. K1 spring will get longer, so it's extension plus y minus k2. Again, it's getting longer. Extension plus y equals my double dot. Now, let's find the extension of the spring. Again, when it sits in equilibrium, we can say the sum of F in y equals may. Remember, we're looking at equilibrium now. It doesn't matter which way we pick positive. Let's pick down. So we're going to have mg minus k1y minus k2y equals m multiplied by 0, because there's no acceleration now. We're looking at equilibrium. If you put the mass on the springs and let it sit there with no motion. From this equation you get mg equals k1y plus k2y. Let's take y as a common factor on this side. So we have k1 plus k2 all multiplied by y equals mg. Therefore, y, which is equal to the extension, just like in the previous example, is mg divided by k1 plus k2. We have to substitute this extension into our equation of motion. That will help us cancel the mg. So, going back to the left, we're going to have mg minus k1, open brackets. The extension is mg over k1 plus k2 plus y, don't forget the y, minus, same thing with the k2, mg all divided by k1 plus k2 plus y. Both springs are longer, so they're both plus y equals my double dot. Now let's go ahead and expand these brackets. So we're going to have mg minus the first one, k1 mg all divided by k1 plus k2 minus k1 y. Same thing with the second bracket, minus k2 mg all divided by k1 plus k2 minus k2y equals my double dot. Now, we can clearly see that these two fractions here have the same denominator. So therefore we can add them together. So minus this, minus that. Let's do that first on this side here. So we're going to have minus k1 mg all divided by k1 plus k2 minus k2 mg. I'm just collecting them together now. I'm not actually doing the addition just yet. k1 plus k2 plus mg minus k1y minus k2y equals my double dot. So let's go ahead and add these two fractions together. So those two fractions left will become minus k1 mg minus k2 mg, all divided by the same denominator, k1 plus k2 plus mg minus k1y minus k2y equals my double dot. Now we can put them together. What I'm going to do is I'm going to find a common factor. So we can clearly see that here the common factor is mg. So we can take the minus outside the bracket as well. So in the end it's going to be minus open bracket k1 plus k2 mg all divided by k1 plus k2. Again, the rest of the equation plus mg minus k1y minus k2y equals my double dot. Now this will cancel with this. So what you'll have left here, you'll have minus mg left here, plus mg, minus mg plus mg equals 0. So therefore, this mg cancels with this mg as well. And you're left with only the remaining terms in the equation, which are these terms here. Now, you'll have two situations. The first situation is if, let's put this here, if k1 equals k2. What you will have is you'll have minus 2ky equals my double dot. And by now we know how to transform this. Divide both sides by m, add 2ky first to both sides. So you're going to have y double dot plus 2k over my equal 0. Now if k1 does not equal k2, then instead you're going to have minus k1 plus k2 all multiplied by y equals my double dot. And by the same merit, you're going to have y double dot plus k1 plus k2 all divided by my equals 0. Both equations are in the form of simple harmonic. So in this final example of the vertical spring mass system, we have a mass here with a spring either side, one on the top, one on the bottom. Now again, I'm going to model the downward vertical motion. You can model the upward, you'll have the exact same expression in the end, y with respect to time. Now you can clearly see that the top spring is going to get longer whilst the bottom spring is going to get compressed. So we know how to deal with that in our equation with the E minus y and the E plus y. First of all, free body diagram. The mass is causing it to move down, mg is the weight. Now, we have two spring forces here. We have the k1x, or k1y in our case, because it's moving in the y direction, pulling it down, and of course the k2y will want to pull it back up towards the top. So let's start by doing our equation of motion. The equation we're going to use is sum of all the forces in y equals ma in the y direction, with down is positive. This is the dynamic equation. This is when it's moving. So it's going to be mg plus k1y minus k2y equals my double dot. Now let's include our extensions, mg, because the spring, the K1 spring, is getting shorter, it's getting compressed, it's going to be K1 extension minus y. Y is the variable, the position, minus K2, open bracket, E plus y, because the K2 spring is getting longer, equals M, y, double dot. Now let's find the extension, just like we did before. We look at the static solution of the system. So again, sum of f in y equals m a y, down positive, doesn't matter because a is going to be 0. So the static equation is going to be mg plus k1y minus k2y equals m multiplied by 0. Rearrange that equation, make y the subject, a little similar to what we did in the last video. So if you're not sure, have a look at all the steps we did there. In the end, you'll have y, which is equal to your extension, is equal to mg, all divided by k2 minus k1. Now that we have our extension, we can substitute it into the equation on the left. So let's go ahead and do that. So we're going to have mg plus k1. Now we know the extension, we just found it. mg all divided by k2 minus k1 minus y minus, same thing on the left side, k2 open bracket mg divided by k2 minus k1 plus y on this side is equal to m y double dot. Now let's go ahead and expand this bracket. So we're going to get mg plus k1 mg all divided by k2 minus k1 minus k1y minus k2 mg all divided by k2 minus k1 minus k2y equals my double dot. Now let's combine those two big fractions together just like we did in the previous video. We've got these two fractions here. They have the same denominator, so we can add their numerators. So let's do that in one step this time. So we're going to have on the top minus, open bracket, k2 minus k1 mg all divided by k2 minus k1 plus mg minus k1y minus k2y equals my double dot. Now you can test that by expanding this bracket. If you expand this bracket, you get minus k2 plus k1, which is what you have here, minus k2 plus k1. So all we've done is combine these two fractions together to make one fraction. Now the reason we did that is because you can clearly see that the k2 minus k1 cancels with that. Then we will be left with minus mg plus mg. So they will also cancel. So that will cancel with that. Minus mg plus mg. And all you're left with is that remaining right terms. So let's bring them together on the left side of the page. So we have minus k1y minus k2y equals my double dot. And we have the same thing as last time. We have two situations. If k1 equals k2, then the equation becomes minus 2ky equals my double dot, and in the end we have the same equation as last time, plus 2k over m y equals 0. Now if k1 does not equal k2, instead you're going to have minus, open bracket, k1 plus k2 y equals my double dot. So in the end you're going to have y double dot plus k1 plus k2 over m y equals 0.